Hello, my name is Alejandro Delgado, and this is my lab on the constant velocity of a ball. In this experiment, we work under the assumption that the ball is moving at a constant velocity, meaning that there's no net force and it only moves in one direction. This is because that when an object is under constant velocity, it's only going to move in one direction, as it is implied by the name constant velocity. A velocity can have a speed of zero, but it could also be changing direction. But in this case, it's going in one direction at the same speed. At least, that's what the parameters of the project are. Because it's assuming that there's no friction and no other outside forces. We have to visually construct a computer model of the motion of a ball moving at a constant velocity and understand how an object moves when there is no net force. At the end of the results, we find that the xt graph, the position versus time graph, is linearly increasing, and the velocity time graph is constant with a slope of zero. A few equations that we're going to need are the average velocity formula, which is the vector of the change of position of the ball over the change in time. This equation was very helpful because the object is moving with no net force, meaning that the average velocity is the same throughout the entire movement of the ball. Another useful equation was the velocity update formula, which helped us find the change of velocity over time. However, there was no change of velocity, so this ended up not being a very useful part of the code, but we needed to include it anyways to show that there was no net force. And the third one we needed was the position update formula, which was helpful as it told us where the ball ended up relative to where it started. Here's the video really quickly. This is the video I used to show how a ball moves under no net force. And here's the data from the tracker that showed me how the ball changed its position over time. These values look a little weird, but these are mostly all just to 10 to the negative 1 power, meaning that the decimals are just shifted one place over. It had a negative velocity because the ball moved from right to left, as you saw in the last video, and tracker reads this as negative. Here are my calculations to find the average velocity of the ball, and it's simply just the position vector of where it started minus the position vector of where it ended, which is Rf minus R1, over the change in time. And as you can see here, the average velocity ended up being negative 0.463 meters per second in the negative x direction. And this equation was useful for our code, as it helped us change the initial condition for the ball. It started off as in the code as being 0, 0, 0, but we had to change this value as the ball needed to have moved somehow. So I changed this to negative 0.463, 0, 0 as the velocity vector, and the position vector to the value of the position that it started according to the tracker. In addition, I had to change a few of the equations in the calculation loop after the while loop was added. So the velocity of the ball equation was changed to parallel the velocity update formula, which was unneeded because there was no net force on the ball. And also the ball position equation, which is to parallel the position update formula shown in a few slides before. And here's the graph from the glow script, which started at time 0 and ended at negative 4.27. It started at, sorry, negative 4.27 times 10 to the negative 3 meters, and its final position at 0.57 seconds at negative 0.26355 meters. A few takeaways from the model and some conclusions I drew from error could be that there are problems with both models, but mainly the problems are that the tracker model may be inaccurate due to clicking errors when setting the x-position of the ball, as you have to actually click where the ball is going and where it is at each time interval. And the glow script computer model can be inaccurate because it works under the assumption that there is no net force acting on it, as I said it to be in the code. If the axis and the tracker video were oriented differently, the velocity would be shown in a different direction on the graph of the vector tracker. This is because velocity is a vector, and it changes when the axes are oriented differently. It would look like a completely different arrow. The only forces that act on the ball, assuming that there's no friction or air resistance, are the force by the ball on the ground, which is the weight, and the force by the ground on the ball, the normal force. These forces cancel out, And we know this simply by just looking at the ball. If these forces did not cancel out, the ball would just fall through the floor.